All right. So let's say I did the sum now n which equals 1 to infinity of -1 to the n divided by n squared. Okay? Now the sum n equals 1 to infinity of the absolute value of -1 to the n now divided by n squared. This is the sum n which equals 1 to infinity of just 1 divided by n squared. All right, so you would say at this point of the problem that, well, 2 is greater than 1, so this is a convergent p-series. Because p equals 2. Okay. All right, so what can we say about this one? We can say, therefore, the sum n equals 1 to infinity of -1 to the nth power divided by n squared is, we're using a abbreviation, absolutely convergent. Okay. So this is an example of an absolutely convergent infinite series. Okay? Okay. Now, let's try another one. The sum n which equals 1 to infinity of -1 to the n divided by the square root of n. Okay. Well, the sum n which equals 1 to infinity of the absolute value of -1 to the n divided by the square root of n, okay? This is going to equal the sum n which equals 1 to infinity of just 1 divided by the square root of n. Okay. Now, 1 divided by the sum n equals 1 to infinity of 1 divided by the square root of n. This is a p-series like our previous problem, but this is a divergent p-series, okay? So, that's a divergent p-series because p is going to equal 1/2. All right? So, what do we say at this point of our problem? Not absolutely convergent. Okay? And so then what you have to do is use, I'll abbreviate this one too, alternating series test. Okay? Now, 1 divided by the square root of n plus 1 is indeed less than 1 divided by the square root of n, and the limit as n tends towards infinity of 1 divided by the square root of n that equals 0. Okay. Then we can say, therefore, conditionally convergent. Okay. So you need the proof that it's not absolutely convergent, and then you need to use the alternating series test to show that it is convergent. And with both of those statements, that's actually proof that this thing is conditionally convergent.